All right, thank you. You might notice the title on the slide is actually a little different than in the the schedule. That's on purpose because we can do more than just fixing bugs with Getafix, although bug fixing is what I'm going to use to explain most of how Getafix works, and I'll come back to other applications right at the very end. One other thing to simplify things for this talk, I'm going to use the words static analyzer warning and bugs interchangeably. So let's start with some motivation here. Static analysis tools are useful for helping developers detect bugs. One tool we use at Facebook is Infer. And in this example, this tool is warning about a potential null dereference. But sometimes showing just a warning isn't enough because even true positives are not acted upon by developers. So showing a fixed suggestion is a great way to increase the actionability of warnings. Yes, and therefore increase their fix rate. So fixed suggestions for these Infer null dereference warnings have been deployed for about a year at Facebook. And during that time, we've shown thousands of fixed suggestions. And if we drill deeper into the reactions from developers, we see that a large fraction of the time, developers simply accept the fix that we make. So why is this impressive? Well, for one thing, we know that developers are really picky. And we know that because another 9% of the time, developers end up making a semantically equivalent fix. For example, inverting if condition and then swapping the then and the else branches. But another reason that it's difficult is that there's simply a lot of ways to address certain warnings like null pointers. And we need to conform to developer tastes. And so here's a sample of the multitude of different ways that developers have fixed null pointer bugs at Facebook. And the variety of different approaches means that it would be difficult to hand code all of the possible different templates that you need to use. But in addition, then you need to predict which of those templates to use given a new bug. But what's interesting here is that when I say these are examples of how developers fixed bugs at Facebook, what I actually mean is that these are suggestions that were made by our Getafix tool and developers accepted and then merged into the code base. So now that we've seen what Getafix can do, let's talk about how it comes up with those fixed suggestions. At a high level, it's a three-step process. First, we're going to take the raw human code changes. We'll turn them into AST edits. We'll then look for patterns in those AST edits. We'll get a set of templates. And then we'll apply those templates to new instances of bugs, get potentially a large set of possible fixes, and we'll rank them by how likely we think that a human would have made that fix. So to start, we'll turn the source code fixes into AST edits. And we'll focus on changes which fixed bugs, as described before. So we'll specifically just focus on commits that fix bugs. In example, we have this one here. We'll take the entire file before and after the commit. We'll parse to a generic AST representation where we just have labels and values for all the nodes in our trees. And this is nice because we can actually be language agnostic. This whole pipeline is language agnostic. We just need to be able to parse. Once we do that, we'll run a tree differencer between these two trees to tell us what changed. And the tree differencer, as part of that process, will figure out mappings between nodes in the before and after. So for example, in this case, it's decided this node marked in orange had its value updated, the node in red was removed, and the two nodes in green were inserted. And now that we've identified which nodes are modified, we want to create small AST edits showing what changed. And so the way we'll do this is we'll go through all of the mappings according to our tree differencer, and we'll create a tree from the before and the after according to those mappings, the subtrees. And the reason we want to do this is so that we can get potentially small localized edits from a larger edit. Potentially, developers make multiple changes in addition to fixing a bug, and we want to be able to learn from not just the entire change, but pieces of the changes. So in this example here, the nodes which are updated are mapped to one another, so we'll create an edit from them. The parents of the updates are mapped to one another as well, so we'll create an edit from them too. The parent of the node which was deleted has a mapping in the after, so we'll make a subtree edit from that, and so on and so on. And we'll do this for all of the mappings for which there's at least one modified node underneath. And once we do this for all of the edits, we'll get this large set of, all of the source code edits, we'll get a large set of AST edits. And next up, we'll look for patterns in those AST edits. So the way we're going to do that is we're going to look through all the edits and find the pair of edits which are most similar. Let's say in this case we pick these two edits right here. And so what we're going to do is we're going to create an abstraction from these edits which basically contains as much information as possible. And so in this case, the structure of these two edits is the same, so we keep that structure. In addition, they both agree on the null and the zero literals, so we'll keep that as well. But in locations where they differ, like such as variable names and method names here, we'll replace them with variables or holes. And then we'll repeat this process on and on, repeatedly picking the most similar pair of human edits or even templates so far. And we'll merge the most similar pair together until the most similar pair is so different according to some heuristics that we'll stop. You can imagine, for example, an edit which deletes a return statement, another one which inserts an if statement are just so different that it doesn't make sense to merge them. And so once we're finished, we'll get this forest of edits here, this hierarchy, going from the raw human changes down at the leaves, and then getting more and more abstract the higher up you go. So this hierarchical clustering is nice, but it really depends on this sort of similarity function, how you decide which two edits are the most similar. And the answer to how we do that is basically it's actually based on the abstraction you get when you merge two edits together. And at a high level, we're preferring abstractions which are less abstract. We want to maintain as much information for as long as we can in our hierarchy. And so then, of course, the question becomes, where does this abstraction come from? The answer is it's a process called Anti-Unification. This idea is actually not ours originally. It came from a separate paper from Rollum et al. Called Quick Fixes, Learning Quick Fixes from Code Repositories. And what anti-unification is it's opposite of unification. Given multiple input trees, you're going to create a single tree which maintains as much structure as possible. And anywhere where the input trees differ, you'll have holes, which you can then substitute subtrees back into to recreate your original trees. So how does this work for our edits? Well, we're going to anti-unify the before trees first, and then the after trees. And one key insight is that we're going to try and reuse any existing holes that we created while merging the before trees while we process the after trees. So that's a lot. Let's go through an example to make that a little more clear. Here we have two edits which we want to try merging together. Here's the AST representation of this first edit. And so as I said, we'll start by merging the befores of both of the edits. And so we'll do a depth first search and basically keep everything in the tree structure until we hit some nodes which differ. So this block node is the same in both. This method call name is the same in both. But then we hit A and C, which are different. So in this case, since they're different, we have to make a hole here. We'll remember it maps to A in the first tree and C in the second tree. We'll then continue along and hit B and D. We can't reuse H0 here since it's a new substitution. So we'll create H1 and remember the substitutions we made there. Then we'll continue to the after trees. We'll do our depth first search until we hit nodes which differ. And here we have A and C. But if we look at our existing substitutions, we realize that's the same thing as H0, so we can actually reuse H0 here. We'll continue along until we hit A and C again. Once again, we can reuse H0. And then we'll hit B and D. Now this, of course, is H1, so we can reuse H1 as well. And then we'll finish up. So if we pair the result of merging the after ASTs with the before ASTs, we now have a single templated pattern which represents both of the edits we started with. And we can now generate candidate fixes by matching the before anywhere into AST of some source code that supposedly has a bug. And everywhere that it matches, we can mutate it into the after. And here's the easier to read source code representation of this abstract edit that we just found. And as I said before, we'll get lots of possible patterns. Here's a couple additional examples here. And the last step is that we're going to apply these mine patterns to new bugs to get potentially a large set of fixes, and then we'll try and rank. So here's an example bug. Here's the three patterns that I just showed before. Let's see what the possible fixes that these patterns will produce is. So we get something like this. We have these three, so we get three matches for the first pattern, or for the third pattern rather, and then one match each for the first and the second pattern. And the challenge for Getafix now is we need to determine how to prioritize these fixes. So we'll actually use a different example here to explain this a little better. So here we have a separate pattern which just says wrap some statement with a null check. And given some code here which has a bug on potential null dereference on this x.f line here, what are the places where this pattern can match? Well, we can wrap x.f, we can wrap this important side effect, or we could possibly wrap this entire while loop that sort of counts according to this pattern. But which of those are actually fixes? Well, we could invoke the tool that said that there's a bug here in the first place, and that would probably tell us that if we wrap just this important side effect, that's not actually going to fix the bug. But if we wrap the entire while loop, well then, I guess that actually does mean this dereference won't happen. So technically that's a fix, but that's not really what we're after here, because a human would probably say there's this important side effect here. So I actually don't think wrapping the entire while loop counts. As a human, I think really just wrapping x.f is good. So what Getafix needs to decide here is hfix. So let's formalize this a little bit. So fix candidates are triples BPZ, which means pattern P applied Z lines away from bug B. So match here is just Getafix enumerating things. Fix requires us to rerun some analysis tool, and so it actually gets a little more expensive there. We're burning CPU cycles. But then finally, hfix at the end is the most expensive. This is where we actually have to show a fix to a developer for them to decide if it's reasonable or not. And so this is actually the most expensive. We want to use our resources wisely. Since the human time is the most expensive, we want to only show at most one fix for each bug to developers so they don't spend all day combing through thousands of fixes. In addition, while we can validate a handful of fixes by rerunning an analyzer, we don't want to validate too many because there is sort of a limit to CPU resources. We don't want all of Facebook's machines to just be spent trying to fix null pointer bugs. And so therefore, that means we need to do our ranking right after we enumerate possible matches. So we want to rank by this conditional probability here. How likely is a match that we found likely to be what a human would do? So we haven't actually seen this particular bug B before, but we can estimate our probability based on our training data. In this case here, btrain is just the examples of fixes we've seen in the past. And so our question is, when P and Z were used to fix bug B, what fraction of the matches were also the human fix? And so something that's nice is in our training data, hfix is actually decidable because it is just the training data, what did humans do? But unfortunately, it's a little slow to compute this at the time that we're trying to make suggestions, and we'd have to look back at our whole set of training data. So it's a little infeasible. But fortunately, we can factor this fraction into 3 scores, which are actually pretty intuitive, as I'll show in an example here, and are pretty easy to compute during training. So let's come back to the example of the possible fixes we had made before. And we'll go through the 3 components of our ranking score. So the first component is simply based on how often we've seen each of these different patterns used in our training data. So maybe in this case, the first pattern is used 30% of the time, second 15, and the last one 40%. Next up, we're going to try and basically prefer patterns which are used in the right location. So for example, the first pattern is basically an inline pattern. So it's almost always happening right at the line where the warning is reported. Second pattern is mostly an inline fix, although it's possible that an if statement wraps multiple lines, so maybe it's not quite as strong as the first one. And in the last case, with our third pattern, there's sort of a distribution of how many lines above a null dereference people insert an early return, so that's why we see some lower values there. But we also see that people never actually fix a null dereference by inserting an early return after the bug. So that's why we get a score of 0 down here. And our last component that we're going to use is basically preferring patterns which have more context and are more specialized, which match in fewer locations. So this pattern P3 here is very general. It just inserts this early return anywhere, so it gets a very low score. This pattern P1 is more specific. It needs to match a method call, so it gets a higher score. And P2 is even more specific because it needs a return statement, and so it gets an even higher score. And if we multiply these up together, then it turns out P1 wins, and so that's good for us here. So as I said before at the start, Getafix can do more than just fix bugs. And learning from code changes sort of allows us to do a lot more than just fixing bugs. So I'm going to share some of our results from bug fixing, as well as some of our vision for what Getafix can help with in the life of developers. And our vision is automating routine engineering work. So if you think about the type of work that engineers do throughout the day, there's sort of a spectrum from sort of routine, monotonous, boring stuff on the left and getting more interesting on the right. And so the sort of thing that we want to do is automate a lot of the routine and boring stuff so people have more time for the more interesting stuff on the right. So let's look at these three categories in detail. The first category we've already talked about quite a bit throughout this talk, but for evaluating our paper, we also looked at error-prone bugs just to see how well things generalize, and sure enough, we do find ways to fix them. And what about the accuracy? How well does this work? Well, we measured our ability to predict human fixes accurately by taking sets of human fixes for all these different categories of bugs, splitting into folds, predicting on like 90% and then training on 90% and then trying to predict the held out set. And these are our top 1 and top 5 accuracy for these different classes of bugs. 10% might look kind of low for null pointer exceptions here, but something that's really important here is we're actually comparing whether or not we get exactly syntactically the same fix as humans. This is our ability to predict that hfix predicate that I showed before. And so 10% isn't actually that bad, especially when you realize that we've been running this in production and 42% of the time, developers are just accepting the fixes that we suggest right away. Another category of routine work that we were trying to help with automating is the process of reviewing code. So remember, as I said, like the input to the system for training is just sets of file pairs. So you can basically give files before and after people responded to code review comments. And if you do that, sure enough, you learn anti-patterns as well as how to address them. So we've done that, and we've rolled out some of those suggestions at Facebook. Finally, one additional option is you can just take the entire commit history as input, just all of the changes throughout the entire commit history and see what's happening. And if you do that, you actually learn refactorings. So in this case, we've found basically people using new modern Java features like catch blocks and Lambda statements and for each statements. So here's the team Getafix. There's myself and Johannes and our manager Satish Chandra. And additionally, Michael Pradel was a visiting professor on sabbatical at Facebook and helped a lot with writing our paper and designing a lot of our experiments. And finally, some related work. As I mentioned before, this Rollum et al. Paper was a heavy inspiration for us, particularly the process of using anti-unification to abstract multiple edits. And at this point, I'll take questions.
Hi, thank you for a great talk. As your bug fix part for the evaluation, as we all know, there are a lot of existing auto fix approaches. Mm-hmm. So do you ever consider to compare your work with them on some data set to,
Yeah, the biggest difference between us and a lot of the existing tools is that as I was saying, our accuracy numbers here are actually our attempts to predict exactly what humans are doing. And pretty much all of the existing tools, as far as I've seen in the literature, are basically using some sort of oracle like a test set or some existing analyzer and just say if the analyzer stops complaining or if the test set now is green, we're not the same, or like we count that as a fix. So it's a little tough to compare based on that. We could potentially compare just using that sort of standard as our standard as well, but we haven't done that yet.
Okay, thank you.
Thank you. It was a great talk. I know this sounded like it was more recent work. Have you done any evaluation, and can you provide numbers on that for the reviewing code and the refactoring?
We haven't. We've sort of deployed some of these patterns at Facebook. We don't have. I don't have the numbers with me right now, but we have seen some positive reactions to them. So, yeah.
So we are doing something similar in the context of refactoring, so in which we actually learn the context from which you can apply the transformation. So do you think that it's relevant in here, or will it work in here, or will it not work?
It depends
Can you
what you
comment
mean
on
by
that?
context. So as I was showing in this example, like when we learn edits, we sort of don't know exactly what the level in the AST that we should be looking at the edits as. So we sort of rely on our hierarchical clustering process to determine what the right level of context is. So basically our definition of context is unmodified nodes. So for example, if you have something like inserting an early return, in a case of null, maybe you learn that it happens before a method call or something like that. That's the type of context we learn. I'm not sure what type of context you're necessarily referring to.
Yeah, so we are using a combinations of like node type and then like the kind of predicate or something like that, a combination of a bunch of things. I don't know, like maybe you guys can try it out to see if it works or not.
Yeah, it's possible we
We can chat
could
offline
use
about that.
some sort of predicates and stuff like that, yeah.
Hi. So you mentioned that between two commits you parse twice and then do a tree diff. Would you also be able to use an incremental parser for this?
Sure. I don't really know too much about incremental parsers, but sounds possible. Does it sort of give you a sense of sort of what's actually changing between them as well? Okay, yeah.
Okay, cool.